A junior engineer changed the A record but left the TTL at 86,400 seconds, 24 hours. Asian ISPs cached the old IP, locking out an entire region. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover how DNS works. DNS stands for Domain Name System. It translates human-readable names like example.com into machine-readable IP addresses. It's a distributed, hierarchical system that replaced the old static HOSDS file, making the internet scalable. Computers communicate using IP addresses, but humans are terrible at remembering numbers. We remember names. DNS bridges this gap. Before DNS, the internet used a single file called HOSDS.txt that was maintained centrally and downloaded nightly. As the internet grew, this became impossible. DNS replaced it with a distributed, hierarchical system. Here's an example of a HOSDS file. It still exists on your machine and can override DNS for local development, but as you can see, it's static and not scalable. DNS is a tree. At the top are 13 root name servers. They don't know every domain, they know where to find the top-level domain servers. TLDs are com, org, etc. Each TLD knows the authoritative name servers for every domain under it. The authoritative name server holds the actual DNS records. Here's the full query flow for www, example, com. The resolver walks the tree, root, TLD, then authoritative. Each step is a referral until the final answer. When your browser needs an IP, it sends a recursive query to a DNS resolver. The resolver does all the walking. It queries root, TLD, and authoritative servers on your behalf. This is called recursion. Alternatively, the resolver can do an iterative query where it asks each server for a referral. Most end-user resolvers use recursion. Using dig with +trace shows the iterative steps. You can see each referral. Root gives TLD, TLD gives authoritative, authoritative gives the final IP. Every DNS response includes a time-to-live value in seconds. This tells the resolver how long to cache the record. Caching is essential. Without it, every page load would trigger a full DNS walk. But caching is also the source of the classic DNS propagation delay myth. There's no central propagation. Each resolver caches independently and respects TTL. You can check the remaining TTL of a cached record using dig. Here, the TTL is 86,342 seconds, meaning it was cached 58 seconds ago. If you need to flush your local cache, use the appropriate command for your OS. DNS records map domain names to various types of data. The most common are for IP4, AAAA for IP6, CNAME for aliases, and MX for mail servers. A common mistake is using a CNAME for the root domain. CNAMEs cannot coexist with other records at the same name. Here's a sample zone file. Notice the SOA record at the top, then NS, A, MX, and TXT records. The CNAME for www2 is fine, but you cannot use a CNAME at the root because it would conflict with SOA and NS. Let's trace what happens when you type www example.com. First, the browser checks its own cache. If not found, it asks the OS, which may have cached from other apps. The OS asks the configured resolver. The resolver checks its cache. If not cached, the resolver queries a root server, then a TLD server, then the authoritative server, and finally returns the IP. Using dig with +stats shows the query time. Here it's 23 milliseconds, which is the time to get a response from the resolver, not the full walk. If the resolver has it cached, it's fast. To see the full iterative walk, use dig +trace. Standard DNS has no authentication. A malicious actor can spoof a DNS response and redirect users to a fake site. DNSSEC adds cryptographic signatures to DNS records, allowing resolvers to verify authenticity. It uses a chain of trust from the root zone down to the domain. You can check if a domain has DNSSEC using dig with +DNSSEC. The add flag in the header means the response was authenticated. If DNSSEC validation fails, you'll see SERVFAIL. This is the same issue we highlighted at the start. Here's exactly why that happened. A junior engineer changed the record for our domain, but left the TTL at 86,400 seconds. The old IP was cached by Asian ISPs. The new IP was only seen by users who had never visited before. Users in Asia couldn't access our SaaS dashboard. The fix is simple. Always lower TTL to 300 seconds at least 24 hours before any DNS change. Then wait for propagation before making the switch. For the current mess, we had to contact major ISP support to manually clear their caches. The key change was setting TTL 300 in the zone file. This is the exact mistake from the incident. The TTL was set to 86,400 seconds, so after changing the record, old cached entries persisted for up to 24 hours. Always lower TTL before making changes. A CNAME at the root domain is invalid per RFC 1034 because it conflicts with other mandatory records like SOA and NS. If you try, most DNS software will ignore the CNAME or cause undefined behavior. MX records will fail because the CNAME takes precedence. Always use an AAAA record for the root. Disabling DNSSEC validation on your resolver to fix SERVFAIL errors is dangerous. You're disabling security. Instead, fix the DNSSEC configuration on your domain. Use tools like DNSVis.net to debug. The article mentions UDP port 53, but modern DNS often uses eDNS0 to support larger responses, e.g., DNSSEC signatures. Without eDNS0, responses over 512 bytes are truncated, forcing a TCP retry. This can cause timeouts if TCP is blocked. Always ensure your resolver and firewall support eDNS0. Use dig plus buff size equals 4096 to test if your resolver supports eDNS0. A successful response includes an opt pseudo section. If you get a truncated reply, TC flag, eDNS0 may be blocked. The article covers DNSSEC for integrity but doesn't mention encryption. DNS queries are sent in plaintext by default, exposing browsing history. DoH and DoT encrypt queries, preventing eavesdropping. Many public resolvers, e.g., Cloudflare 1111, Google 8888, support both. Use dig at 1111 plus HTTPS to test DoH. Here are the essential debugging commands. Use dig to check basic resolution, specific record types, trace the full path, or query a specific name server. These commands will help you diagnose most DNS issues. Let's run through some common interview questions. What's the difference between recursive and iterative queries? Recursion is done by resolver. Iteration is client following referrals. When would you use low TTL versus high TTL? Low TTL for dynamic environments, high TTL for stable records. What happens with a CNAME at the root domain? Invalid per RFC 1034, breaks MX and other records. And a few frequently asked questions. How does DNS work? Queries hierarchy, cache, resolver, root, TLD, authoritative. What's the difference between A and CNAME? A maps to IP, CNAME maps to another domain. Why don't DNS changes propagate instantly? Each resolver caches until TTL expires. To recap, DNS is a hierarchical, distributed system. TTL controls caching duration, so always lower it before plan changes. CNAME records cannot be used at the root domain. DNSSEC prevents cache poisoning but adds complexity. Enable it for critical domains. Ready to go deeper? Up next, TCP versus UDP, then the OSI model, then HTTP 1.1 vs HTTP 2 versus HTTP 3, QUIC. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.